Delaney. This is August 8th, 2012. I teach at South High School in Minneapolis, the wonderful South High School. And my demonstration today is on a relationship between conservation of energy and projectile motion. And I haven't seen this used anywhere, so I had fun doing this. I presented this about 11 years ago in San Diego at a physics convention, and it was well received. Okay, to start, if you can see this column of water, I have a hose directed vertically, and at the bottom it has kinetic energy at no potential. At the top it has no kinetic energy left. At the very top it all potential. So I set the two equal. Now the height of this is 216 centimeters. As you can see, I have it on the board here, 216 centimeters. And then I use this equation for the velocity for the 2gh. And that comes from projectile motion, conservation of kinetic energy, kinetic plus potential, kinetic plus potential, 1/2 mv squared plus 0 equals 0 plus mgh. Solving that equation, I got that equation b equals 2gh. I'm putting in that value for h of 216 and using c, 980 centimeters per second squared. I get 651 centimeters per second. I have an angle of elevation that I'm going to set at 53 degrees. And the y component of that at sine of 53 times the 651 will give me 391 centimeters per second. The target is 127 centimeters below where the initial velocity is, below the muzzle. And so if I set, using this equation for the final position of y, equals y initial, where it's located, component y times t plus 1/2 h squared. I solve that for t, I get 1.05 seconds, or a negative 0.025 seconds. Of course, that would be the two zeros for this equation, 1 0 for a time that would be before my timing started the muzzle. So this is the time we want. Now to get my range, and that's really what we're looking for, is how far does this thing shoot. I noticed my son parked his motorcycle there, but I did this experiment yesterday, so we're kind of rehashing it. And yesterday I found that where it landed was well in front of where he put his motorcycle, so I didn't bother him to move it. Okay, so my Vx, that component, cosine of that same angle of elevation times the initial velocity, I get 521 centimeters per second. And so for that time, times that component velocity, I predict 547 centimeters. The result I got was 495. Percent error, 10%. Now I'm going to move this out of the way so that you can see that parabola. And I'm going to take this last bit of time in the tape to simply reset the angle that cannon is firing at, that water cannon. I'm using a easel that's used for a transit level in construction. The nice thing about the easel, the legs are precisely 5 feet long. So if I move it till it has an angle, a vertical component of 4 feet, 4 feet up, 5 feet hypotenuse, I get my 53 degree angle. So let me move this, and I'm going to just change the angle that is shooting at, and you'll see the parabola. You can see the nice parabolic shape of the trajectory. And I am missing the motorcycle, flashing it a little bit. But it turned out to be 16 feet 3 inches, or 495 centimeters for the range from where the muzzle is to where it hits the concrete. So that's it. Thank you very much.